Welcome back to my channel FusyBots. So today we are going to learn about joint space planning. Basically, in any robotic arm we have two types of plannings. One is the joint space planning and another Cartesian space planning. So today we are going to learn joint space planning, that too with the trapezoidal velocity profile. So I will show you what a trapezoidal velocity profile basically means. So this is the basic UI I have made to control the robot. These are the desired joint angles. Now the currently my robot is at home position where all the angles are 0. So this is the home position, and now these are the angles I want to send it to. This is the maximum velocity and the maximum acceleration is 2, that is in radian per second square. So let's start. So you will see that it has started moving. Now you can see in the plot juggler that the velocity profile it follows is a trapezoidal velocity profile. Here you can see that all the joints that follow the trapezoidal velocity profile. Now I will send it to home. So basically for home the angles will be 0 and a default velocity and acceleration. So you can see it come to home. Now you can see that the velocity profile is triangular. Why? Because the joint with the maximum distance doesn't have enough time to follow a trapezoidal profile, so it has followed triangular profile. So there are only two phases, one is the acceleration phase and another is the deceleration phase. So you might be a bit confused about what I'm talking about this, so let's go to the mathematics behind this and then we will jump on to the code. So now we'll starting the mathematics behind this trapezoidal velocity profile. So we know when we are following a trapezoidal velocity profile, it means that velocity will have three phases. One is the acceleration phase, then we have a constant velocity phase, and then we have a deceleration phase. So what we are going to do now, basically we will use simple equations of motion. You know that the equation of motion states that s is equal to ut plus half at square. So if we apply it in this phase, you know that the velocity is starting from 0. So this equation will become s is equal to half at square. So this is the basic equation we will use during acceleration phase. Then comes the constant velocity phase. This is the cruising phase. So in the cruising phase, this is already the motion done during the acceleration phase. You see that this is now t acceleration. Now the remaining motion will be Vmax into t, that is ut basically, because the velocity will be constant for time t. So then we will going to use this equation for the cruising phase. And then coming to the deceleration phase. In deceleration phase we have already moved this distance, and now this is the distance which is moved during deceleration phase. So this is basically how our mathematics work during trapezoidal velocity profile. But now how to do it for different joints. For example, we have 6 joints. So I will give you an idea that if we have 6 joints and the joint with maximum distance is following this profile, then other joints have to fit inside this profile only. For example, one joint will do like, the time for each phase will be same, like this. So each joint has to fit inside this profile only. If we have, for example, in our case we have 6 joints, so all the 6 joints has to fit inside this profile only, like this. So how do we ensure that? So how I have ensured it, basically after finding this s, I will find a point in between the trajectory, and that point will basically define according to the joint which has to follow maximum distance. So I will make a ratio. So a ratio will be like distance of joint j divided by max distance, and this max distance is basically the distance that is the distance a joint has to follow which has the maximum distance. So for example, we have 6 joints, one joint 2 3 4 5 6. One is going from 0 to 90 degree, other is 0 to 20 degree, another one 0 to minus 30, another one 0 to 180 degree, another one 0 to 20 degree, next is minus 10 degree. So we know that this is the joint which has to follow maximum distance. So I will define everything for this. For this joint the ratio will be 1, and for other joints they will fit inside this ratio. For example, some has 0.8 ratio, so it will follow this profile. Some has 0.5 ratio, though it will follow this profile. And how will I ensure that in my equations? So what I will do, I will find a point that is basically the start angle, that what is the start angle for that joint, plus plus this s which we have find above, but that s into this ratio. So this s, see, when the ratio will be 1, everything everything will be added to the start angle. But when the ratio is, for example, 0.8, then it will be all the joints will be managed according to the joint which has to follow maximum distance. So this is the case when initially we have zero velocity, starting from zero velocity. So that is how we are handling this. Now one more issue, for we have to also check whether our joint will able to follow three profiles. For example, this may also a case when it will only accelerate and then decelerate. So this can also be the case when there is not when there is no sufficient distance. So like how to deal with this and how to find. So we have maximum acceleration and maximum velocity given from user side. So what we will do is we will just find that how much time it will take to reach to the maximum acceleration. So that is basically time is what, basically the velocity, that is the maximum velocity minus 0, because it is always starting from 0, divided by a max. So we will get some time here, and we know that maximum acceleration and deceleration will be same. So deceleration time will be equal to acceleration time. Now we have to see whether we have t cruise time with us or not. That is basically whether it is possible to do this d cruise or not. So how do we find that? So that is also find with the help of the joint which has to follow maximum distance. So what we will do, we know that this total distance or the maximum distance basically is area under the curve. This is area under curve. So for example, we assume that it will follow a trapezoidal profile. So these three areas it has to follow. So this is basically a triangle, that is half into t acceleration into height, that is v max, plus then we have this area, this is a square, so v max into t, rectangle basically. Then we have half into t deceleration into v max. This is the area of this curve. We know that these two areas are same, so this will be t acceleration into v max plus v max into t, and this is the total distance. Now we'll find t cruise from here, that is distance minus t acceleration into v max whole divided by v max. If we find that this t cruise is greater than 0, that means we will have three phases. Otherwise we will have only two phase, and this is decided basically on the joint which has to follow maximum distance. So this is the mathematics behind this. So after finding this s, what we have to do, we have to find a point, for example this point. So what is this point? That is the start angle. So this is basically a velocity profile. If you will see the distance profile, it is something like this. If my joint angle is starting from 0, so start angle plus this ratio into s. So this s will be added to the start angle depending on what ratio it is. So this ratio will basically fit all the joints inside this curve like this. All the joints will be fitted inside this curve like this. So this ratio is important to understand, and what is this ratio is the distance this joint has to follow divided by max distance. For example, this distance, particular distance has to follow pi by 2 radians, but the maximum distance is pi radians. So this is 1 by 2. So this is the mathematics behind this. As now we have gone through the mathematics behind the trapezoidal velocity profile, now I assume that you know how that is happening. Let's go through the code of the trapezoidal velocity profile and have a glimpse like how to write a code for that. So first starting with what I have explained you in the mathematics. So this is basically that part. So what we are doing, we have three phases: acceleration phase, cruising phase, and then deceleration phase. And you can see these are the same equation I have explained you in the mathematics. So by explaining this code, what I mean to say, I will give you a glimpse of how to write a code uh, means mathematical part is done, but how to write a code, how to write an executable for that. So that how I have written is, so basically there are two things you can do. One is the online planning, that in which whenever a user give a point, the planning is done in online mode. And one is the offline planning. In offline planning, all the points are calculated first, and depending on whether the trajectory is possible or not, we will follow further. So I have followed the offline planning one. So there is nothing much. You have to just make a subscriber to joint states and a publisher to joint states. That is the main thing. So we require one publisher, one subscriber. Then we want to know the current joint states, desired joint states, and initial joint state. These are the things we require for calling the function. So once we get any point, so basically I will get something from user. So this is the function to get points from user. Whenever I will get anything from user, what I will do, I will call my execute trajectory function. So, and take care of one thing that I have started in a thread. Why, I will explain you later. So what will this execute trajectory function do? This will just execute, this will first find all the points of the trajectory, and then it will execute the trajectory. So what it will do basically, it has already find all the trajectory points in this array, that is basically here, the compute trajectory points. When all the trajectory points are computed, and how it is computed, that is basically the same mathematics I have shown you earlier. So this is the mathematics, and I also explained you how to find whether the full trapezoidal velocity is possible or not. So this is the code behind that, whether it is possible or not. If it is not possible, then what we will do, we will follow a triangular profile. That is the case. So you can see this part, that we have calculated the acceleration, then distance acceleration. If this distance is smaller than twice of distance of acceleration, that means what we have to do, we have to scale it to maintain a trapezoidal velocity profile. And that too is basically not a trapezoidal profile, that is basically a triangular profile. And after computing these points, what I will do is basically I will execute those points and I will publish those points. So this is what I have done, and velocity I have calculated just to show you that it is following a trapezoidal velocity profile or not. So I think we have a just overview through the code, and you have understood the code. So that's it from my side. Thank you for watching the video.